Hi, and welcome to the Foundations course Lesson 8, Thoroughly Designing a Study, Part B on Etiological Research. So today we are going to discuss etiology studies, and we will start with an overview of etiological research. But remember that the GCR study design process tells us to always first think about a research question and then design the data collection and data analysis process, followed by determining a required sample size and then writing the necessary study documents. And today we will focus on the study design process. So the aim of etiological research is to determine causes of disease or risk factors. And in the data collection, a typical study design is either a prospective or retrospective cohort study, but some studies use a case control study as an alternative study design. And the typical outcome assessed is disease occurrence or survival. And typical data analyses are logistic regression modeling, resulting in odds ratios, or Cox proportional hazards modeling, resulting in hazard ratios, and sometimes a risk ratio is determined. When using an observational study design such as etiological research, one should follow the Strobe guidelines, and you can find the specific guidelines on the Equator network. But when you have followed these lessons on study design and looked into the GCR statistics study design tool, then you will already have learned what the most important reporting factors are in these guidelines. So let's put etiology research into context. Where does it actually fit in the scientific process? It oftentimes all starts in preclinical studies where new mechanisms of pathology are uncovered. And once they have been firmly established, this new knowledge feeds into the first clinical etiological cohort studies, where the proposed risk factors are assessed. And oftentimes, multiple of these studies need to replicate these findings. And eventually, this feeds into the development of new therapeutic options through screening programs, behavioral interventions, and drug development, where if a therapeutic option has been discovered that helps to mitigate disease through the proposed mechanisms of pathology and risk factors, the real risk factor causality can be confirmed. And sometimes new mechanisms of pathology are proposed from some of these clinical cohort studies where new risk factors may be uncovered, which can feed into the preclinical study loop that may use this new knowledge to test the proposed mechanisms of pathology. Now let's move on to how to perform etiological research. And we'll start with the traditional approach, where I will try to show you what's wrong in my opinion. The typical research question in the traditional approach is a certain determinant a risk factor for developing a certain outcome in a certain domain, meaning the study population and setting? And as the typical study design, retrospective cohort studies are used. And the data collection oftentimes is based on the selection of patients who were potentially at risk of developing a disease. So here we actually start from the pool of patients that have developed the disease and then work backwards to finding that common pool, and then perform a retrospective electronic patient chart review to collect the determinants of interest and other baseline characteristics. And eventually, some studies obtain additional information through questionnaires. But we have already learned that all of these factors increase the risk of bias in a study. And in the data analysis, oftentimes no sample size calculation is performed, and missing data are just simply ignored. Furthermore, variables of interest are selected from the database based on significant associations with the outcome in a univariable analysis, so that only the significant factors are entered in a multivariable regression model, and that multivariable regression model oftentimes is heavily overfitted when the sample size is limited. And the thing that researchers seem to be most interested in is whether a statistically significant relationship can be established between the determinant and outcome of interest in one of multiple tested multivariable models. Because if researchers are honest, oftentimes they will admit that they have developed multiple multivariable models with various modeling approaches just to search for significant relationships. And in the conclusion of the traditional etiological research, in the case of no significant relationship, it is claimed that the determinant is not an independent risk factor for outcome, but we have already learned that absence of evidence is not evidence of no relationship. And in the case of a significant relationship, the determinant is claimed to be an independent risk factor for outcome, ignoring the influences of confounding, overfitting of models, and the lack of generalizability in the study findings. Okay, now that we have seen what the traditional approach to etiological research is, let's look at the GCR approach, in which I will give you advice on how to do things a little bit better. The first point is to know when to perform an etiological study and when not to, and which study design to use. So the point here being that determining risk factors for disease in an observational study is difficult, since it is prone to many sources of bias. And maybe you should only attempt this study design when you have access to a very large cohort. So that could also mean that you look for other researchers to collaborate with in a multi-center study, or reach out to institutions with good registries like governmental institutions or health insurance companies, etc. And when the disease is very rare and there's no other way of studying, it is defendable to use a case control study. But if the disease is not too rare, it's better to use a prospective cohort study, or if that's really not feasible, a retrospective cohort study with a high quality source for the data. And you should follow the STROBE statement. And one thing I haven't explained yet is that these epidemiology statements have been written up to make sure that authors use this list and report their methodology and study findings according to the statement, so that both the quality and the transparency of the studies are improved. But of course, you can also use these kind of epidemiology statements to your advantage during the design phase, because they also explain which choices in the design phase are considered to be better than others. And with regard to the choice of the study design, we need to acknowledge that the strength of evidence differs between the prospective cohort study, retrospective cohort study, and the case control study. There are advantages and disadvantages to all of these study designs as previously discussed. And for prospective cohort studies, we should note that all patients that are potentially at risk need to be included and followed up long enough. But that, of course, is very time and finance costly. Whereas in retrospective cohort studies, bias is a huge problem and needs to be addressed. And you need a very large cohort with clearly defined endpoints and a good quality source for the data. And in case control studies, you should especially think of a good way to select the controls, for example, at random from the same population. Now, the second point brought forward by the GCR approach is that we should predict potential sources of bias ahead of time and then think of ways to avoid them in our study design. And of course, we have the three types of bias. Selection bias can be an important problem in etiological studies where the study population is not representative. And we have already discussed this in the previous lesson, but in general, in selection bias, the sample doesn't seem to be random. So we need to think about a good source for recruiting our target patients and record all patient characteristics of all eligible patients. Attrition bias may occur if there is selective loss to follow-up. So the thing that we at least need to do is record the reasons for dropout or loss to follow-up as far as possible. Now, in information bias, the data collection differs between patients, distorting the determinant-outcome relationship. And thus, we should train data collectors to be objective and standardize the data collection process. Recall bias is a problem where there's differential recall of exposures between patients, and a way to circumvent this is to use more objective proxy variables. And observational bias occurs if participants change their behavior when they are observed, and we could use incomplete informing about the study goal or blinding to attack this problem. An observer bias is the type of bias that occurs if the outcome assessor is influenced by knowledge of the patient status. And most of the time it is possible to blind the outcome assessor, so this should be done. And if not, then you can think of using more objective outcomes like mortality, for example, that do not allow room for interpretation on the side of the observer. And confounding, of course, is a huge problem in etiological studies, where we are not actually measuring the association between the variable under evaluation or risk factor in these types of studies and the outcome of interest, but we are measuring the association with another variable that might even be a causal factor that is related to the outcome of interest. We should definitely make a list of potential confounders ahead of time and measure them if that's possible in our cohort study, and then use a multivariable regression and or stratified analysis to try to adjust for confounding, and obviously cautiously limit our conclusions to the population that we actually studied. Now, point 3 is that in etiology research, we should assume association until there is sufficient evidence outside your own study to imply causation. And the goal of a single study should be to enhance understanding of the disease and potential risk factors, but it shouldn't be to prove a causal relationship. Since many consecutive studies need to replicate findings before a causal relationship between risk factor and disease will be established. And Sir Austin Bradford Hill published a very interesting paper called The Environment and Disease Association or Causation in the Proceedings of the Royal Society of Medicine in 1965 that is worth a read. And here he lists a couple of aspects of association that, when present together, might indicate that a risk factor actually is a causal factor of disease. And the first aspect to consider is the strength of the association. Associations with a stronger relative risk measure, such as the risk ratio, odds ratio, or hazards ratio above 2, for example, or maybe even 5 or 10, tend to more likely be a causal factor. And the second aspect to consider is the consistency across studies, and then specifically across different investigators, places, circumstances, and time. If there is consistency, then a causal association is more likely. The third aspect is the specificity. With very specific associations, a causal association is more likely. And the fourth aspect is temporality. So you might want to ask yourself which is the cart and which is the horse. And this is not always very clear, but if there is a clear temporal association where a relationship in the reverse direction would not make sense, then that also points towards a causal relationship. A biological gradient, such as a dose-response relationship, is another important aspect that might point towards a cause and effect relationship. Then the biological plausibility. If there's a known or understood mechanism, then that obviously supports the plausibility of cause and effect. Coherence. So if there's no conflict with natural history or the biology of the disease, then that supports a cause and effect relationship. And experiment. So if preventive action is taken to take away the risk factor, then does that prevent the disease, or can you somehow treat the risk factor to mitigate the disease? Then that also strongly supports a cause and effect relationship. Some people refer to this list as the Bradford-Hill criteria, but Bradford-Hill himself doesn't like that designation because he tells us that none of my 9 viewpoints can be required as a sine qua non. What they can do with greater or less strength is to help us make up our minds on the fundamental question: is there any other way of explaining the set of facts before us? Is there any other answer equally or more likely than cause and effect? And actually, that's a very powerful question to ask yourself. And you should ask yourself that question in all etiological research. Furthermore, he also states that no formal tests of significance can answer those questions, referring to hypothesis testing and p-values. Such tests can and should remind us of the effects that the play of chance can create, and they will instruct us in the likely magnitude of those effects. But beyond that, they contribute nothing to the proof of our hypotheses. So we shouldn't make the mistake of thinking that statistical significance tells us something about potential cause and effect relationships. Now, the fourth point of the GCR approach is to follow a thoroughly pre-planned analysis. And the first part to focus on is the outcome. The outcome of interest dictates the type of analysis that is required. So if we want to look at the proportion of diseased or deceased patients at a certain time interval, then logistic regression would make sense. If we want to look at a time to event outcome, then survival analysis would make sense. And if we want to look at patient-reported outcomes such as quality of life over time, then a longitudinal analysis such as a mixed effects regression model makes sense. Especially in cardiovascular medicine, complex composite endpoints are very popular, and this means that researchers pool multiple outcomes such as, for example, mortality, myocardial infarction, or stroke together and analyze them as if they were one outcome. But I would advise against using composite endpoints whenever possible, because they tend to complicate the research more than it helps to clarify the exact relationship between determinants and one outcome. On the determinants, you should ask yourself, what is your variable of interest and what are potential confounders? And an important point with regards to this is that you should not categorize continuous or count data when putting them into your model, because you will lose precious data and power. Another problem with categorization of continuous data is that it allows you to select an arbitrary cutoff for the different categories, and you can actually manipulate that cutoff in a way that will make you find a significant association. In some situations, it is defendable to use categorized continuous data, especially in variables where it is common clinical practice to use certain categories. There are some more specific points with regard to the data analysis. You should adjust for known confounders in a multivariable model, but also for plausible unknown potential confounders. And you need at least 10 events per variable in the model as a guideline for your sample size determination. And one specific thing to note here is that in a logistic regression model, the lowest number of outcomes, so that can either be the number of events or the number of non-events, dictate this rule. And you should not try to fit the best model by eliminating non-significant factors, since the point here is not prediction but statistical adjustment for confounding. And you should ask yourself whether there are important effect modifiers or interaction terms, and whether the risk factor applies to your entire study population. When reporting the data and drawing a conclusion on your study, remember that statistical significance and p-values are the least interesting finding of your study. But if you do report p-values, use absolute numbers instead of cutoffs such as p lower than 0.01 or p above 0.05. And if you use a regression model for your analysis, chances are that you will obtain a relative measure of risk as your result, such as an odds ratio, a hazards ratio, etc. Try to convey what that means in terms of absolute risk to the individuals of interest. And remember that odds ratios and hazards ratio can be different from relative risk, especially if the outcome is not that rare. And quantify your measure of uncertainty. So always use measures like the 95% confidence interval. All right, that's it for lesson 8. Thoroughly designing a study, part B on etiological research. Next up will be diagnostic research.